Good afternoon, everyone. Thank you so much for joining us today. We are going to get started in just a moment. We're just letting a few more attendees join us, and then we will get rolling. Alrighty, so with that, thank you all for joining us for our Thought Leader Series webinar. Today we're going to be talking about hypoxia in a subtropical estuary and the development of a regional monitoring network. So I hope you're excited to learn more about how dissolved oxygen data is being used to inform estuary restoration efforts. Next slide. All right, excellent. Thank you so much. And I am your host, Taryn Picard. I am the Global Product Marketing Manager at Onset Computer for our Hobo product line. I have been working with customers for over 9 years now, helping them to select the best Hobo data logger for their application. And I absolutely love hearing about how our data loggers are being used. So I'm very excited today to be learning more about our U26 dissolved oxygen logger and how it's been helping with some estuary monitoring. Next slide. So this webinar is going to run for approximately 45 minutes. We will do our best to save about 15 minutes at the end to answer some of your questions. If you do have a burning question during the webinar, please don't hold back. Over on the right-hand side of your screen, in the control panel there, you can type in your question and we can try to answer it for you during the webinar, or we'll wait till the end and answer those questions when we can. This webinar is being recorded, so you will receive a link to it afterwards. So if you have to leave early, or if you missed something, you will have that advantage to go back and review this webinar in the future. So a little bit about us. Onset Computer is the home of the Hobo data logger. We actually design and manufacture data loggers right there in that building, which is located on Cape Cod. But our data loggers are sold around the world. We have a global network of distributors. And we're really focusing in on not only designing and manufacturing reliable data loggers, but also doing it at a high quality level. So we are ISO 9001-2015 certified, and we also follow lean manufacturing processes. Jumping on here, so today's presenter, I'm excited to introduce Austin Fox. He is the assistant professor of Ocean and Engineering Marine Science at Florida Institute of Technology. He is an experienced biochemist, educator, and project manager. Currently, Austin is focused on impacts of eutrophication on internal nutrient recycling in estuaries and the coastal ocean. Dr. Fox was recently recognized as one of the top performing researchers at Florida Tech, so I'm pleased to have him presenting for us today. And along with Dr. Fox, we have Tyler, who will be joining us from the Brevard Zoo, who is the ROS permitting coordinator. So we have a special guest today, which is very exciting.
Well, thank you, Taryn, and thank you everybody for coming. So I'm going to turn off my camera so you're not distracted by my bobbing head up in the corner. So we're talking today about hypoxia in a subtropical estuary and the development of a regional monitoring network. And this is such a powerful tool, and we've been really happy to work with Onset and work with our partners. And so Tyler will talk a little bit about just using multi-data producers to expand this network and create a really powerful regional network. And so Taryn introduced me, but I'm Austin Fox, a researcher at Florida Institute of Technology. And so here's just a few pictures of students and I working in the field. And right in the middle there, you'll see one of the U26 loggers in one of our benthic chambers. My research interests are focused on nutrient cycling and trace metals. And so we look at the interactions of things like trace metals with nutrients and how internal recycling contributes to eutrophication. And so an outline for what we're going to talk about today, the Indian River Lagoon. And so this is an estuary. It's in our backyard here in Florida, but it gives us a really good laboratory to study these global processes, right? So we can think about processes that are being observed in estuaries around the world. So we're going to talk about population growth and how that's impacting nutrient loading, how these nutrient loads have led to regime shifts in estuaries around the globe, from things like seagrass dominated estuaries to algae dominated. And then why DO, right? Why are we so interested in dissolved oxygen? We'll lead from dissolved oxygen to talk about nutrient cycling, just the importance of DO and how it regulates nutrient cycling in these estuaries. We'll look at a little bit of the data we're collecting, just kind of the power of the network and where we're headed with it. I'll hand it off to Tyler for a moment to talk about some of the other applications of this data. And then one of the really important considerations are just the logistics and QA/QC, so the quality assurance and quality control. And then finally, you can throw tomatoes or whatever you do at the end of presentations. So I'm sure all of you are aware that there's been this global decline in estuarine health, and there are papers coming out all the time talking about the losses of seagrasses. And this loss of seagrass is so important for so many reasons, right? We're seeing habitat loss, right? We're seeing the loss of fisheries. In this region, we've seen a huge decline in fisheries, and that's happening all over the world. We're seeing losses of charismatic megafauna, and if you're familiar with Florida, you've probably heard about the loss of things like manatees. And so when we lose the food source, right, we can no longer support a large population of grazers, and so we kind of have this shift in carrying capacities that can lead to these mass mortality events. We also have a loss and or a change in the bacterial communities, and so that kind of ties into the nutrient cycling that I'm going to talk about today. So the Indian Lagoon, where is it? It is not in that little red box that moved. We're on the central east coast of Florida. So if you look at the kind of satellite image there that's zoomed in a little bit more, that's where we are. The little point sticking out to the east there, that's Kennedy Space Center, where we're launching rockets pretty much weekly at this point. But this region is the Indian Lagoon system. And so when we kind of come down to ground level, right, why do we care about this system? It's beautiful. It contributes so much to our economy. People love to live on it, recreate on it. And this system, the Indian Lagoon, is 156 miles along the central east coast of Florida. It spans both tropical and subtropical climates, leading to incredible biodiversity. We have all kinds of animal species, plant species, so it's a really interesting place to live and work and play. But one of the challenges is we have limited connectivity to coastal oceans, right? We have 90 miles between inlets, and so a lot of the contaminants, a lot of the nutrients that come into the system stay in the system for a long time. And so we're studying kind of the impacts of increased development. And the Indian Lagoon is an estuary of national significance, and so it's really important to protect the species that are living here, and to do that we need to better understand what's going on in this system. And so globally, right, we're seeing these declines in seagrass habitats, and a lot of it, much of it, is related to population growth. And so you're seeing here a section of the lagoon in 1984 and 2022, and so a huge difference in infrastructure. And when we look at the population of Brevard County, so that's the county we're in, the start of the space program led to this dramatic increase in population that's continued ever since. And with kind of this new space race occurring, we're seeing the population take off from even where it is today. And so historically, right, this lagoon and lagoons all over the world are really dynamic systems. And we've had lots of impacts from infrastructure. And so we've had historically the opening and closing of inlets. And so inlets are a break in a barrier island system that allow exchange of water between the lagoon in this case on the left, and the ocean, in this case the Atlantic Ocean, on the right. And so these inlets naturally open and close, and where you see wide areas, right, we see wide areas of these barrier islands, that's historic flood shoals. And so that's sand that has come in from the Atlantic Ocean to virtually basically infill these lagoons. And so as we built infrastructure along the coast, we stabilize these inlets. We're not allowing them to form where they may have in the past. And we're also pumping a lot of the sediments that come in this stabilized inlet back out so we can maintain navigational channels. This lack of sand, right, and this change in the sediment dynamics has really hypothetically played into some of the changes in nutrient cycling. And so we'll talk a little bit about that coming up. And so again, pumping that sand out of the lagoon has removed some of this healthy sediment that would otherwise come in. Also, if you look at the flood shoals that are forming on the lagoon side of the barrier island, that's those kind of sandy, shallow areas. We decided we wanted to live in Florida. We also decided we didn't like mosquitoes. And so we dredged channels through a lot of these wetlands. We created upland dredge spoil islands with channels weaving in between them. And this process has changed a lot of the ecosystem services and altered the nutrient dynamics in these regions. Other things that have happened is Florida was a swamp. We've drained large patches of Florida in order to do agriculture and to build infrastructure. And so in 1922, they built a canal. It's towards the bottom of your screen. You can't see it on here, but that big lake connecting it to the lagoon that drained 30 billion gallons of fresh water per year into our lagoon through channelized systems. And so this water is no longer sitting and being processed in shallow marshes. It's draining through channelized systems directly into the lagoon. We'll talk a little bit about the importance of that later on. And also, right, historically, there weren't subbasins. And so when you look at this picture on the right, you're seeing causeways or bridges that are built with earthen structures that have significantly restricted the circulation, right? This is restricting the movement of sediments, and it's facilitating low energy environments in the corners where we can accumulate fine-grained sediments. And so legacy loads, right? We've made improvements in the amount of nutrients and the amount of stuff that we're allowing to enter the system, but we've had decades, right? A century of inputting huge amounts of material. And so one example of that is in 1990, we passed the Indian River Lagoon Act that banned the discharge of wastewater directly into the lagoon. And so by 1996, we'd stopped this, but a lot of damage had already been done, right? We put tons of material into the system that accumulated somewhere. And so when we built these causeways, and so you can see the earthen bits of that structure there, and we look at the bathymetry, you see deep deposits. We've created these dredged holes. And many of these, it depends on where they are with the hydrology that's going on, but many of these have accumulated what is locally referred to as muck, or muddy sediments that's very organic rich. It's decomposing, releasing lots of nutrients into the system. And so this muck, this is a picture of muck in the background. I put my hand in it to give you some contrast. Otherwise, it just kind of looks like an ugly background. But there's nothing living in this material other than some bacteria, right? And so this muck does a few bad things, right? It's composed of fine-grained organic rich sediment. The given empirical values, this is from Treffery 1989, has a very high water content. It's fine-grained, 60% silt and clay, and it's organic rich, greater than 10% organic matter. And this decomposes, releasing nitrogen and phosphorus into overlying water. And so as the extent of these muck deposits has grown, that muck has become a significant source of dissolved nutrients into the overlying water. And so this is from recent estimates. Muck is contributing in the Banana River, which is kind of that easternmost section of the Indian River. Muck contributes between 40 and 50% of the total inputs of nitrogen and phosphorus to this system. And so this accumulation and this change in the sediments has been really important towards nutrient cycling and adding nutrients to the system. And so what's the impact of these nutrients? If we look at the relative biomass of photosynthesizing organisms, right, seagrasses versus macroalgae and phytoplankton, versus as we increase nutrient concentrations, right, as you increase nutrients, you get an initial benefit to the seagrasses because they're no longer nutrient limited, but you also start to increase the amount of the macroalgae and the phytoplankton, right? And as you increase the amount of phytoplankton and macroalgae, you start to have competition for either space with the macroalgae or blocking of light as we have phytoplankton and increased turbidity. Beyond some threshold, when we start to see hypereutrophic conditions, right, we start to actually see a die-off of the seagrasses because of that competition. And so those are kind of idealized images from the literature. But if we look at data from the Indian River Lagoon itself, right, you can see that seagrasses were doing pretty well until about 2010, and we've had the significant drop off in both median transect length and percent cover. And at the same time, if you look at the graph on the right from Phillips et al. 2021, you see about that same time we saw a dramatic increase in the average phytoplankton biomass. So this fits very well that model of the regime shifts seen in the literature. And so this loss of seagrasses has led to this crisis that you've probably all heard of, the unusual mortality event for manatees. And when you hear about it, you see these beautiful pictures like this. And this doesn't necessarily show reality. And so I have a video here that is from this system showing what the reality actually is. And this is a manatee trying to find grasses, but it's pretty much eating dirt. And it's picking up some of the grass clippings that blew in as they mowed that adjacent one. And so there's so many different things that we can talk about associated with this video, but I'm going to keep going in the context of oxygen and nutrients. And so why dissolved oxygen? So here's another kind of model of the eutrophication process, where as we increase nutrient loading, we can view that as a hammer pounding on the system, and grazing by things like zooplankton can kind of buffer that increased nutrient loading. But as we see that increase in nutrients, we have the enhanced growth of macroalgae and microalgae. That can lead to increased turbidity, right? Those algal cells block light from reaching the bottom. That can cause turbidity and even increased resuspension of the sediments as we lose those seagrass beds. As we lose seagrass beds, right, we have increased growth of macroalgae and increased sediment erosion and resuspension that then feed back into those first two kind of swinging pendulums. When we think about how can we monitor these changes, right, what do we choose to monitor when we look at water quality? If we look at enhanced growth of macroalgae during daylight hours, this is going to add oxygen to the system. If we look at increased turbidity and benthic respiration, these are going to consume oxygen from the system. And the net result is, as we have eutrophication progress in a system, we see destabilized dissolved oxygen concentrations. We see larger diel or diurnal fluctuations. And so hypoxia, right? Eutrophication can lead to hypoxia. There are a few different types of hypoxia, but right here I'm showing this is kind of the classic image of hypoxia. We have fresh river water containing nutrients coming in. We have sunlight and oxygen coming in at the surface, leading to incredible productivity in the surface ocean, right? As we have algal cells being produced in the surface ocean, we actually see very high oxygen concentrations. Those dying and decaying algal cells, as well as fecal pellets from the zooplankton, sink to the bottom where we have decomposition, right? Below that photic zone, we actually have decomposition exceeding photosynthesis, and we have low oxygen events that we term hypoxia. And historically, hypoxia is defined as less than 2 milligrams per liter. Fish can swim away. Those benthic organisms, many of them that can't escape, die. And when we look in systems like our Indian Lagoon, it's very common to see dead benthic fauna and not necessarily a fish kill. The fish kills are the things that make the news, but it's very frequent that we see these mortality events that more or less go unnoticed. And so some of the different kinds of hypoxia, right? Permanent hypoxia, these are in systems where the hypoxic area is effectively there all the time. Seasonal hypoxia, that's what we're seeing in places like the Gulf of Mexico with the dead zone. We have episodic, which is days to weeks in duration. This is the kind of hypoxia that we're starting to see more frequently in places like the Indian Lagoon, these shallower, well-mixed systems where we don't necessarily have as much stratification. And also, as we destabilize DO concentrations, we see diel or diurnal, day to night hypoxia. So we see very high concentrations of dissolved oxygen during the day, and it can get very low overnight and even go hypoxic or anoxic. And so water column respiration and fluxes, right? How can we quantify these things? And so we've used our Hobo U26 DO data loggers in benthic and water column chambers to measure the lagoon respiration. And so Lagoon restoration, our median value is 0.2 milligrams per liter per hour. That means 50% of our samples are consuming more than that 0.2 milligrams per liter per hour. So in a 12-hour dark cycle, right, we should see on average, or the median value is 2 to 3 milligrams per liter decrease in DO. In Port Canaveral, so this is in seawater in the port, so this is not the best seawater. If we move offshore, it's quite a bit lower than this, but in adjacent seawater, we're seeing less than or about half of the respiration rate. That means that in a 12-hour dark cycle, we're seeing a decrease of only about 1.2 milligrams per liter. So when we look at these respiration rates over time, you see the ocean values, that's that kind of green colored line in the background, it doesn't show as large of diurnal fluctuations. Where the lagoon side, we're seeing in this case, right, this is one of those above median value times, like a 4, 5, 6 milligram per liter diurnal swing. And so why is this bad? Right? It doesn't take much. So a small perturbation can lead to hypoxia or anoxia. And in fact, that's what we see, right? So what you're looking at on the left is kind of zoomed in on a single week. When we look at a month long, you see that immediately following this week, there was actually a hypoxic event. And in fact, we go there and we saw fish kill, right? And so how can we start to explain these phenomena? Right. And so just while I'm mentioning this, nutrient fluxes, those nitrogen and phosphorus fluxes are proportional to the respiration. When we see high respiration rates, we see high uptake and recycling of these nutrients. And so can we explain these events? And so this is an oversimplification, but it demonstrates how susceptible these unstable systems are to hypoxic and anoxic events. And so this is looking at some weather data, and that hypoxic event immediately followed a cloudy day, right? And so where we have these algal dominated systems, where we have unstable DO concentrations, it doesn't take much. A single cloudy day can throw the system into hypoxia. And so when we start to track this, what existing data are available? And so there are a few different networks out there. Most of these sensors are located at kind of the middle of the water column at depths ranging between about 0.4 and 1.9 meters, and that varies as the water level in the lagoon adjusts following trends in coastal sea level. So most of these mid-depth sensors, they're great for getting a general picture of what's going on in the water column. They're really great because they're providing continuous real-time data. And these are wonderful because it gives us the potential to respond, right? If we had things like aerators, we could watch this data, watch a hypoxic event forming, and go turn on those aerators and do something about it. But one of the things that's missing is a picture of what's happening at the sediment water interface where this geochemistry is actually happening. And so in the bottom water, that's where we're seeing most of the geochemistry occurring. That's where we're seeing nutrient fluxes occurring. That's where these benthic fauna are responding to changes in DO. And this is how we can determine suitability for restoration, right? We're putting clams, we're putting oysters on the bottom, and so we want to know what's going on there. It's also a great way to evaluate the success of projects. Can we see a more stabilized dissolved oxygen profile after restoration has occurred? Finally, one of the things that we really like about our HOBO sensors, these continuous non-real-time data, is that we can actually quality control it before we ever release the data to the public, right? So we are forced to go to the sites, collect the data, do the quality control before releasing it. Where with some of these other networks where you can go on and view it live, there are lots of advantages, but occasionally there are some QA/QC issues using that real-time data. And so with this relatively low cost, continuous non-real time, we're able to put the cost that would go into really expensive real-time monitoring into expanding the network to have more sites. And so you can see the network that we've started to build with the zoo, and there's actually a lot more points that should be coming onto this map in the next couple of months. And so why does this matter towards nutrient cycling, right? If we look at a well-mixed water column and we look at sensor placement, it doesn't really matter, right? You can put the sensor at the top or the bottom, and it doesn't matter. But if we look at what happens in the sediments, sediments have organic matter in them. That organic matter is decomposing through bacterial processes, releasing reduced nitrogen in the form of ammonium and phosphorus or phosphate in the form of phosphorus. In the sediments, these diffuse upwards, and if we have an oxic layer of surface sediments, we have this process, nitrification, that converts that reduced ammonium to things like nitrate and nitrite, and those can then be subsequently reduced to N2 gas that is removed from the system. It's removed into the atmosphere. In the case of phosphate, we have amorphous iron and aluminum hydroxides that can sorb that phosphate, collecting it in the sediments or sequestering in the sediments, effectively rendering it non-bioavailable, where it would eventually be buried in the sediments. When, however, we have hypoxic events at the bottom, right, we lose that surface oxic layer, and that ammonium and that phosphate diffuse upwards into the water column, where it's bioavailable to algal species. Right. And so to put this kind of conceptual diagram into application, this is one of our continuous monitoring sites. The data you're looking at right now is from the St. John's River Water Management District. This is continuously monitored at a mid-depth. And so if I put on top of this our phosphorus fluxes determined using benthic chambers, you notice there are 2 points that are very high and positive fluxes. This first one corresponds very nicely with a hypoxic event, right? The sediments went hypoxic, it released some of that previously bound phosphorus. Looking at this next point, right, we have a very high flux, and using this mid-depth data, it does not appear to correspond to any kind of hypoxic event. Fortunately, at this site, a month beforehand, we had deployed one of our bottom water hobo sensors, and we actually captured a hypoxic event that helps to explain that very high and positive flux. And so it's really cool that using these bottom water DO sensors, we can start to explain nutrient cycling. And this really points out the importance of sensor placement. And so we're starting to put either sensors at multiple depths or using our sensors at the bottom and somebody else's at the top. And so, like phosphorus, ammonium fluxes, when we see those hypoxic events, the nitrogen fluxes are coming out as ammonium, that reduced nitrogen species. And the combination of phosphorus fluxes and ammonium fluxes support things like HAB species. And in the lagoon, we see things like Oreaumbra lagunensis. It's a brown tide, it blocks light, blooms in really high abundances. When there's lots of ammonia available. So in these healthy sediments, we're seeing these ammonia fluxes actually into the sediments replaced with nitrate fluxes outwards. So I'm going to keep moving. That was looking at some of the really cool geochemical processes, but there's so many things we're learning from this network. This is looking at depth. So this is just at the bottom and at those higher St. John's sensors. And what we're seeing is that there are a lot of events, that pink line, right, the bottom of the water column is going hypoxic much more frequently than we would have anticipated just using those mid-depth sensors. And so this is really pointing out the need for a bottom water sensor to look at the geochemistry. Also looking at the bottom type, right, as we see the accumulation of muck, we put sensors out, and the muck has a much higher sediment oxygen demand. And so we're seeing much lower DO concentrations directly over the muck. And the reason that I'm showing you this is we're trying to understand, do the impacts of that muck extend beyond the physical presence of the muck, right? Is the muck consuming oxygen from the adjacent water column? And if we restore those mucky areas, will we see a benefit in the adjacent sandy areas? Ocean versus lagoon. So this is showing just how dynamic and how large those fluctuations are in the lagoon relative to the healthier seawater in Port Canaveral. And then this is just a really cool example of, this is in Cocoa Beach. This is one area that's been selected for restoration. And you can see that this site has pretty low on average dissolved oxygen, and it experiences pretty long-term or weeks-long hypoxic events. So this area is not conducive to things like oyster restoration, but it is conducive to removing some of that muck. And so it's really great that we have data now to support the site selections that we've made. And so we've created this collective DO network of sensors, right? It creates this really powerful tool for understanding the geochemistry, helping select sites for restoration. And so I'm going to turn it over right now to one of my colleagues, Tyler. Actually, I will turn it over to him in just a second to talk about what the Brevard Zoo is doing. And so my questions, right, is what is the extent of hypoxia in the lagoon? This is something that nobody knows right now, and what you're looking at is a picture of the dead zone in the Gulf of Mexico. This is seasonal hypoxia, so it's pretty easy to go out and over the course of a couple of weeks do surveys throughout the region and identify the size of it. So in the lagoon, because it doesn't last as long, because it's more transient, we need to rely on things like these sensors and a really high resolution network of these sensors to be able to address those questions. And so in my opinion, understanding this question, what is the extent, is one of the most important questions towards understanding the system, plus selecting restoration sites and quantifying and improving outcomes associated with those questions. So nutrient load models, so there are lots of people trying to model things, and these models are only as good as the data used to make them. And so we need really high resolution data for sediment water interface, and this network is absolutely helping to improve those models. So this plays into what Tyler's going to talk about in just a second, but benthic organisms have limited tolerance towards hypoxia. And so this applies to everything, even the seagrasses, right? So we've seen limited success of some current restoration projects, and this is likely linked to limited data availability. And so Tyler will talk more about that HSI. And then with seagrasses, right, they don't necessarily need tons of oxygen, they're producing oxygen, but when we see places with continuous low oxygen, we start to see things like hydrogen sulfide that can be toxic to those seagrasses. And so I want to kind of end this part of this talk with that we can understand the natural system to promote successful restoration. And so as these areas of hypoxia expand, they inhibit those natural processes that help to remove nitrogen. They decrease the sorption capacity of the sediments, leading to higher concentrations of dissolved phosphorus in the overlying water. And so one of my goals is to grow this network, promote collaboration among organizations, because collectively we can learn a lot more than when we're working independently. And so currently we've brought in Brevard Zoo. We also have Satellite Beach collecting their own data, and all of this data the QA/QC has managed through a single source to ensure data quality. So Tyler, you want to go ahead?
Yeah, I can. So as Austin just said, I'm Tyler Cravancia, and I am the permitting coordinator for Restore Our Shores at the Brevard Zoo. The Restore Our Shores program is a conservation program at the Brevard Zoo that seeks to restore natural habitat throughout the lagoon and is specifically lagoon focused. So we do a lot of work with oysters, clams, mangroves, and we're getting into seagrass. My role is environmental permitting and the monitoring of our projects. And I am a former student in Austin's lab. And upon getting here, I realized that a lot of the stuff that I had learned with working with sensors could be applicable to the work we do in the lagoon. And so I wanted to help grow that network to understand our projects, answer questions, and in a cost-effective way. So to go into a little bit more detail, our main type of project is subtidal oyster reef. And our main successes with projects have been near historic reef locations, like currently living reefs in the lagoon. And while these projects are amazing and we've had a lot of recent success with those projects, we also want to keep growing our amount of reef. And so we want to make the best decisions in order to pick those sites. And to do that, we worked with Brevard County to make a habitat suitability index for oysters. And while that has been incredibly helpful for site selection and I think improved our projects massively, the actual dissolved oxygen baselines are not there. So we do have, as Austin kind of talked about in his presentation, in his part of the presentation, we have continuous data that's from the middle of the water column, and we have single point measurements from these locations, but we don't have a continuous bottom water like database that we can refer to when we're selecting our sites, basically. If you want to, yeah. So DO is essential for success, but prior to the creation of that network, we just didn't have the ability to do so. And so as we continue to look for new project sites, if you want to keep hitting forward on that, yeah. We want to use dissolved oxygen to use for the extent of hypoxia, salinity for looking at the impacts of looking for high salinity to account for boring sponge, which because our reefs are subtidal is a problem that they will specifically face, and depth, which relates to oyster survivability and recruitment. And on this photo, if you want to go back for a second, Austin, and just some of the photos here, the top photo is our Rickman Park corral that we made. So it's a subtidal reef with loose shell that we just installed. And basically, to the right shows an example of some of the data that we have been collecting for this network. And the bottom sensor on the left is actually a water level sensor, which is something that we've been really excited to get out for the ones looking at oyster site selection, just because of the importance of that recruitment. Next slide. So much like oysters, clams and seagrass lack those kind of baselines, and they have different tolerances, and there's little insight into what conditions they can actually tolerate in the IRL. Seagrass coverage, as Austin said, has decreased, and past restoration efforts even kind of lack those baselines of, or to even explain die-offs. So for example, the main one that we think about with DO is if there's a high or a low DO signal, it could be the impact of hydrogen sulfide in the sediment. And obviously, every species of seagrass and clams as well are going to have different salinity tolerances and DO tolerances. So using that in order to improve or understand better how we can select for those sites, I think is super important. And the sensor on the bottom is a salinity sensor, and I would say that of the sensors we're using for our network for clams in the future, I think we really want to use salinity just because of we're already learning how intolerant of low salinity they can be. So that's just kind of a quick look at some of the stuff that we do for our sensors, and we're hoping to keep growing the network because it provides a lot of value for a relatively low cost. So I can turn it back over to Austin now.
Thanks, Tyler. And so I'm going to try to get through this part quickly because I know some of you might have questions, but it's so important to work with other people because this data is not only valuable to one person. And so I just thought it was worth talking about building this network and some of the logistical considerations. And so the things we think about are fouling, so both biofouling and sediment fouling, and then some of the field deployment techniques. So we went through a lot of trial and error to figure out what really works, and then QA/QC and ensuring data quality. So just some of the things that we talk about. So I've included here the DO Hobo logger manual, at least the top of it, just to say that we're going to reference back to that as we go through these next few slides. So preparing sensors for deployment in the manual, right? One of the things that you're recommended to do is use an anti-fouling guard. And so Onset sells these. We wrap them with additional foil ourselves to help the anti-fouling, because fouling is not your friend. That's one of the things that will challenge us. And so anti-fouling guards are so important. And then along with those, we use some additional anti-fouling things. We use anti-fouling paint on our drilled PVC housings. And so these came about with quite a bit of trial and error. If anybody's interested, I can send you some more information on how exactly we make them. But there's a lot of kind of clever things that go into this design. And so these anti-fouling guards and using PVC housings come directly from that Hobo manual. And this was designed for our U26 loggers and that have kind of that tapered end. Those pressure and the salinity sensors don't fit into this module, but what we've done is we just replaced the top part. We unscrew the top, replace it with a drilled cap that's been dipped in anti-fouling paint. And that works really well, and it makes it so that when we're in the field servicing our sensors, we don't have to have different sizes of the PVC housings. Pretty much everything is interchangeable for all of the different sensors that we use. And so happy to answer questions about that. Deployment, so the top of these housings that you just saw get screwed onto these T's. It's open at the bottom, and so as long as we have circulation at both ends, it's worked really well. We've had very few fouling issues. We use chains to attach it to typically something like a dock. We do use cinder blocks with floats out in the open regions. And I've included the treble hook here because we went through a lot of trial and error with securing these things, making them kind of invisible to the public. And so lots of different things that I'm happy to talk more about if anybody has individual questions. Final thing that I want to talk about, when you have multi-data producers, and so we've been kind of hesitant to just get lots of people involved because it's so hard to make sure we're getting good data quality. So we've come up with some procedures that have worked really well for us. And this comes from the onset manual, but I want to point out a few things that we do. When we get a new sensor face, right, we do that lab calibration at 100% and 0% prior to deployment, and we inspect the sensor face for any kind of damage or fouling or any of that stuff. And we inspect it prior to the first deployment, after retrieval, and prior to cleaning, because we can see if there's any kind of film or any biofouling that would impact the readings. We also look at it again after cleaning and before redeployment. And then we use the lab calibration function. So I know Onset has the field calibration. We use that also, but we primarily use the lab calibration even in the field. We do this following the cap initialization, immediately prior to deployments. And then we don't save the calibration, but we put the boot back on, let it come to equilibrium immediately after retrieval when the sensor face is still dirty. And I will show you some of the values. This is the DO concentration from the logger at saturation, and this is DO concentration calculated at saturation. And we're looking to make sure that those values are still the same, right? If we have a large amount of fouling, those numbers are going to be different. But we compare those to the accuracy of the logger, and in very few cases, right, we've taken lots of steps towards anti-fouling, we take lots of steps towards keeping these things clean. We don't really have to do any corrections, and we really try to avoid, even though they have some really cool tools in the Dissolved Oxygen Assistant, we try to avoid having to use those field calibration steps other than as a quality control step. And so we check it again after retrieval, then we clean it, recalibrate everything prior to redeployment. We also use those secondary values. So this is using a sonde or a second sensor to do those field calibration values, but we typically don't need them, but we like to have them as quality control points pretty much anytime we can. And so I know there's been a ton of information. I kind of flew through this end part. Last slide is talking about the Dissolved Oxygen Assistant. It's something that's available in the HoboWare Pro. We kind of avoided this for a while, and then we realized this is so important to be able to adjust for salinity, right, using those U24 loggers, and through barometric pressure using the U20s. It's so easy to do with their assistant. And like I said, we can adjust for drift using their field calibration, but we typically don't need to with the kind of fouling procedures that we've taken into account. And so thank you all very much for attending. I hope we've been able to kind of show you how we can use these sensors and some of the logistics. This is a grassroots effort, so if anybody's in Florida and wants to get involved and contribute to this growing network, send me an email, let me know. I'd like to thank Florida Tech, right? We've had funding from the National Estuary Program, that's the One Lagoon. Satellite Beach has actually purchased their own sensors to contribute to the network. Brevard Zoo has done the same thing. We've had funding from Brevard County, the state of Florida, and Florida Department of Education that have in some way contributed to the development of this network. So thank you all. I guess.
Great job, Austin. Thank you so much. And I think the one question that rolled in, you've already done a great job of answering. It was just asking you to talk a little bit more about how you deploy the sensors, and that was before you would went over those slides. So unless anyone else has any questions, and I don't see any coming in, Thank you so much for presenting today. We really appreciate it. This was very educational and very enjoyable.
Thank you. Yeah, if somebody has more questions, because I went through that very quickly, if you want to know about the dimensions and what exactly we use, send me an email and I'm happy to get that information to you.
Excellent. And we do have one quick question. Sue just put one in. How far off the bottom are the SONs deployed? And I think she's referring to the data loggers there, unless are you using SONs as well?
No, so the hobo sensors, that's a great question. And the initial idea, we had floats on these to make them pointed vertically, which would put the sensor face roughly 20 to 25 centimeters above the bottom. However, now we've removed a lot of those floats so that the sensors are laying horizontal. It's within 3 to 5 centimeters of the bottom. And I don't know if it's a secret, but there's actually that helps with our fouling issues. If you look at the chains or the floats that we use, there's a whole lot of fouling higher in the water column. So by putting these things very near the bottom, fouling is much less of an issue.
Excellent. And two more questions. How many years is the study that you're doing?
So that's a fantastic question. We started development of this, like I said, it's kind of a grassroots effort, and we get, so we started in 2019 with a couple of sensors. It has grown, and we have funding for another year or so, and we're hoping to be able to continue this basically indefinitely. Our goal is eventually to create maps of kind of the hypoxic zones in the lagoon and how it changes over time.
Excellent. And do you have any type of an automated routine or a script to QC the raw DO and temperature data?
So that's a great question. We have, like I said, we have very careful, we use those field calibrations. And so when we collect the hobos, we check the final readings against a reading that we take with another sonde at the time of both deployment and retrieval. And basically those have to be within the accuracy of the hobo itself. We then can use the dissolved oxygen assistant, but we also run, as we graph all of the data, we look at for trends. So we look at just for rapid shifts. So occasionally you'll see some value where there's an error, it goes to -999, or a start time might not line up with a finish. And in those cases, people can try to figure it out, but we effectively, if we've had something fill with mud, we just don't use that bit of data. So yeah, things we're able to find by effectively throwing some data trend analysis on the data set itself. I don't know if that was clear enough. But.
We have a couple of questions, so I'm just going to kind of group them together around cleaning and calibration. Do you have a set schedule, or how often do you recommend doing that?
That's a great question. And we have been successful with a roughly monthly maintenance routine. And part of that is because of the anti-fouling procedures we've taken. So we've been able to get away with a month. There are times of year where we go every 2 weeks or so. So sometimes in the summer months, we see a little bit more fouling. But we've been able to get away with a month. And we have actually been really successful we have extra sensors. And so we basically take a new sensor, we swap it out with the one that's there, so that we've been able to go through the full lab calibration before redeploying. And then even if we don't have enough, because right as we have 25 sensors out, we don't have 25 extras, but we collect one, we do the lab calibration kind of during transit to the next site, and that's worked really well for us. The sensor faces you can actually pull off and swap, and so if there's any kind of fouling, which is very rare with the way we've done things, we bring the sensor faces back to the lab, kind of soak them in the vinegar solution like the manual says, and clean them, because if you try to scrape it off in the field, you will damage the sensor faces. And so it's better to have an extra sensor that you can swap when you have those minor bits of fouling.
Excellent. Thank you so much. And I've got kind of a slew of questions here, but some of them are more specific to other people's applications. So I would also encourage anyone, if you have questions or if I see here questions that could be answered by one of the hobo application experts, I will have someone follow up with you. So there's some questions specific to, use of the DO logger in a lake and things of that nature, and we will certainly reach back out to you. Also, a question about the battery life for the dissolved oxygen data logger. It has an average battery life of 3 years with a 5-minute logging rate, and that does still depend a little bit about depend a little bit on your environment. And I'll just throw out one more question here. Do you recalibrate in the field if you swap the sensor cap?
So that's a great question.
I'm pretty sure we tell you have to in the manual.
Yeah. So if a sensor cap is changed in any form, it is recalibrated, yes, to both the 100% and 0 during the initial calibration.
Awesome. Thank you so much, Austin. And
And
again,
then,
if I missed, oh, go ahead if you have some more on
well,
that.
so you mentioned the battery life, and we do, so for a lot of the other experiments we do, we have these log every minute, but for our field deployments, we're logging every hour. And so their 3 years is based on that kind of 5-minute interval. So we've had really good battery life success. We've not yet had a sensor. We've had these going for some of them now for 3 years. We've not had any battery issues.
Excellent. That's fantastic to hear, and I appreciate you sharing that feedback. So with that, I think we can wrap things up. And again, if I didn't get a chance to answer some of the very specific questions that are related to someone's application, I'll make sure we have someone follow back up with you, or you can always reach out to Austin directly if you have any additional questions as well. Excellent. All right. Well, thank you again. Really appreciate Austin, you and Tyler taking some time today to present with us. And with that, would like to wish everybody a great afternoon.
Well, thank you all. I appreciate you listening to what we have to say.
Yeah, thank you.